Greetings and welcome back. Recently we've been looking at the reaction between an alpha carbon, that is to say a carbon right next to a carbonyl, with a base. Bases can pull those hydrogens off, giving us a C- that is stabilized through resonance at that alpha position, that is to say alpha relative to a carbonyl. Well, today we're going to be looking at some very special reactions in which a CH that is alpha to not just one carbonyl, but two carbonyls can easily be deprotonated by a base, and there are some really cool things that we can do with this. So I'm going to finish drawing this and ramble on for a second. And there we go. So let's go from there. We'll see that when we have a double alpha, there's a lot of really neat things we can do. In the acetoacetic ester synthesis, we start off with a starting material that looks like this. It's two carbonyls spaced apart from each other and an ethyl ester. So if you look at what we have this two carbon chunk right here, which is an acetyl group, and then we have that same thing right next door, two carbon chunk, and so this is acetoacetic ester. That central spot, the one right here, is alpha to both carbonyls, and therefore it is extremely acidic. We will add in the first step an ethyl oxide or ethoxide in the presence of ethanol. The reason that we add this specific base is that this specific base, if it performs a transesterification with the ester we already have, would trade an OCH2CH3 for an OCH2CH3, so it wouldn't change anything. The reason we use ethanol is that if this ethoxide grabbed the hydrogen from an ethanol, you would generate another ethoxide and another ethanol. So essentially, those guys just won't react in any productive way with each other. So, in the first step, we'll use this base to pull that hydrogen off, generating a carbanion at that central spot right there. That carbanion is a very strong nucleophile that is doubly stabilized by resonance. Whenever you're alpha to a carbonyl, you stabilize a C- through resonance. If you're alpha to two carbonyls, you stabilize through resonance in two directions, and therefore this is an incredibly stable but still reactive species. In the second step, we can add an alkyl halide. Alkyl halide is always going to be a good electrophile, and therefore my nucleophile can attack the electrophile and kick off a leaving group. That will just make a new carbon-carbon bond between that central position, which I had previously removed the hydrogen from, and my new R group. If you'd like to, because there's still one more hydrogen there, you can always repeat steps 1 and 2 if you'd like. And by doing so, you can add a second alkyl group to that central spot. All right, but we'll ignore that for the second. You can do that if you'd like. The third step is we just put this into a little bit of aqueous acid. The aqueous acid will convert the ester into a carboxylic acid, looking like this. This is a reaction that we have seen in the last week. We can convert an ester into a carboxylic acid very easily. And then the carboxylic acid can be decarboxylated because of its proximity to this carbonyl over here. Essentially what happens is that guy comes off, the electrons come down to that position, which would give you a C- that is stabilized by being alpha to that carbonyl, and we're able to have this guy removed as carbon dioxide. By removing CO2, which bubbles off as a gas, this last step is completely irreversible. So in other words, this entire reaction proceeds very readily with very good yield and will always give you a chunk that looks like this. Essentially, it is a 3-carbon chain, the carbonyl at the center, so basically it's going to give you this thing as an acetone, with an R attached. And we start off with basically an acetone attached to an ester. The ester will be eliminated, and yet we will attach any R group we want at that position right there. So this is functionally a very high yield, very easy reaction that lets us make a new carbon-carbon bond. And in this case, it's always going to be at a carbon right next to an acetone, or basically on one side of an acetone, to an R group of our choosing. The second and final specialty reaction that we will do today is malonic ester synthesis. Malonic acid is a 3-carbon diacid, so the IUPAC name of this would be propane dioic acid. And so propane dioic acid is malonic acid. But this is malonic ester, so instead of being an acid, both sides are ethyl esters. Once again, we have that spot in the center that is alpha to both carbonyls, and therefore would be extremely acidic. Once again, our first step is to add ethoxide, usually like sodium ethoxide, in the presence of ethanol. And that will remove the hydrogen through an acid-base reaction from that central spot, giving us a C- or a carbon nucleophile right in the center. Once again, we can add in an Rx of our choosing, an alkyl halide, and this carbon nucleophile will attack the carbon electrophile and kick off the leaving group, giving us a new R group bound by a new carbon-carbon bond in the very center of this molecule. Oops, there's an O there. All right. And once again, if you'd like to, you can repeat steps 1 and 2, since we have a hydrogen there that is right in the middle. So I'm going to just say again that we can possibly repeat 1 and 2. All right. From that point, we will do this third step. It's the exact same step as before, a little bit of acid and water. And what it will do is, since we have 2 esters, we will convert both of them into carboxylic acids. And we will still have that R group attached. All right, but instead of removing both of those, we will only see the removal of one of these carboxylates. You can't remove both because the ability to remove the first one depends on you making a C- that's next to a carbonyl. So after we remove the first one as CO2 gas, which would bubble out, we would be done. You can't put a C- right there unless you have a carbonyl. So we can't take this part off because it would just generate a C- all by itself, which is incredibly unstable. So therefore, we're done. So the difference between the malonic ester synthesis and the acetoacetic acid synthesis is that instead of having a 3-carbon chunk here, you basically have a 2-carbon carboxylic acid here at the end. So we can look at these guys backwards, and we'll do that in a second. But essentially both of these reactions let you convert a starting material with a couple carbons into a product that has a new carbon-carbon bond. And both of them do it irreversibly, giving you very good yields. So just to imagine these guys backwards, if you ever wanted to make a molecule that was a long-chain carboxylic acid, so let's say this guy right here, we could do that through the malonic ester synthesis by making this bond right here. What happened in the malonic ester synthesis is I started with a long-chain ester, well, a diester, and in this case what I want to add is a 1, 2, 3, 4, 5 carbon chain to it. So in my first step of this guy, I would add a base. In the second step, I would want to add that 5-carbon alkyl halide. That's 5 carbons right there. In the third step, I would add a little bit of aqueous acid. And so what would happen is that you would take this part off, you take the entire ester part off of one side, and you would attach that nucleophile to that electrophile. So that's how we can imagine doing this reaction in reverse. Essentially, it lets us make a longer or larger carboxylic acid. The acetoacetic acid synthesis is good for making something like, let's say, this guy, which would be a longer chain, basically acetone. So here is my little acetone fragment right here on the left. There's my little acetone fragment, and I can attach it to this guy over there. And so my starting materials would be that acetoacetic ester right here. Once again, this big chunk right here, that ester, is going to be removed. And the first step was a base. The second step is an alkyl halide. So in this case, I want to add a 1 carbon plus a benzene ring. So I'll use bromine. And then in the third step, I will use acid plus water. All right. And so at the end, I would end up attaching this spot that was alpha to both of those to my alkyl halide and making a larger chain. So the point of both of these reactions is that I can use them to make much longer carbon chains by selectively alkylating a spot that is either right next to a carboxylic acid or right next to a 3-carbon ketone. Thank you very much. Bring any questions you have to class, and we will practice this both forwards and backwards.